Okay, so let's get started. We are talking about ARQ protocols, retransmission protocols, with the purpose of providing a service that delivers service data units error-free, in order, and without duplication. Before we start, actually, there's some announcements. So next week is a special week when it comes to lectures. We have guest lectures on Monday and a video lecture on Thursday. So let's start with the guest lectures here. So if you remember, we have, we will have 3 guest lectures in the same on Monday. It's going to be one on smart grid, one on process control, and one on e-health. These are all integral parts of the course, so it's not just for your pure enjoyment. It will be something that will show up on the quiz and the exam, and also one of these topics you should choose for the third part of the project. So going to the guest lectures, there is a great way of figuring out which topic that interests you the most, and then also to get some insights in what to do for the third part of the project. So please go and look at these. There are 3 experts. Yes?
Will they be available on ping pong as well?
The slides and so forth, and
like you do, like
video. Yeah, that's the plan. I haven't gotten confirmation of the third lecture yet, but 2 of them for sure. But anyway, so please go and see and look at them. They're experts, and also they're invited, so it's kind of nice if one guy is coming from Stockholm solely for this, right? So if there were 5 people in the audience, I don't know. Anyway, so that would be nice. And then you need to sign up for the topic, the part 3 topic. It will open up on Wednesday, say at noon. Shoaib, is that okay?
That is on Monday, then the registration will be open one day after the...
Is that so? Yeah. Okay, so this should be not Wednesday, should be Tuesday? Okay. Let's send out an email about this, yeah. And you do that at ping pong. And it's first come, first serve, so if you have your favorite topics, please sign up early.
So the lectures actually are before the sign up for the different projects?
That's right.
And they're all at the same time?
Yeah, so it's there are 3 lectures and they're 30 minutes each. So it's 30 minutes and then 2 times 15 and 30 minutes. So it's 2 times 45 minutes, one event on Monday. Right, so and then there is a 4th lecture here also. So these are the 3 topics, and then there is one on traffic safety, and it's a lecture that I recorded myself, since I'm working a little bit on this also. So you can view that at ping pong. You don't have to look at it on Thursday. You can view it whenever, right? And you don't have to be in the room, obviously. You can do it anytime. There won't be anybody in the room, by the way, in the lecture halls. Yeah. Questions about guest lectures and the project, part 3? Okay. Then today I will have me and Shoaib, we will meet the student representatives for mid-course evaluation and things like that. So any feedback on the course is, of course, highly appreciated here. Okay, so review. ARQ protocols, or retransmission protocols, is what we are looking at. Used to provide a service that delivers service data units error-free, without duplication, and in order. The key components in any ARQ protocol is that we need some type of error detection in order to verify that things are correct at the receiving end. And to do that, we use error detection code, for instance, parity check codes, internet checksum, or CRCs, or something else. Which one we choose here depends a little bit on how crucial it is to actually find all the frames that are in error, and also a little bit on what we think that the error probability in transmission will be. So for good channels, we can use weak codes like parity check codes. For bad channels, we need something more powerful like a CRC code. We also need sequence numbers, and that basically to keep track of the service data units, so we are delivering them in order and also without duplications. We need some type of timeout mechanism at the transmitter so that we automatically retransmit frames that we don't receive acknowledgements of, because the frames might get lost, and the acknowledgements might also get lost. And the acknowledgements are also an integral part of this, and that's a way for the receiver to inform the transmitter that it's actually received a service data unit. And the combination of these then forms an ARQ protocol, and there are many different types of protocols here. So we talked about the stop and wait protocol, and the main principle, without going into all the nitty-gritty details, but the main principle is that we send a single service data unit with a sequence number and error detection bits, and we retransmit that when if a timeout expires. At the receiver end, we accept error-free frames only. We only process those. The other ones we ignore. And not only do they need to be error-free, they also have to have the right sequence number. And if that is the case, it's both error-free and with the right sequence number, then we send an acknowledgement to the receiver. And then the receiver can send the next service data unit. So I don't know why we have this in two slides. Okay, but anyway, so here is the basic idea, just what I said earlier. Then there is a go back N, is another protocol. And the idea here is to modify the stop and wait transmitter to transmit several service data units at the same time, or consecutively. With the same time, I mean without waiting for acknowledgement. Stop and wait sends a service data unit, and then do nothing until it gets an acknowledgement. Okay, except when there is timeout, it sends it again, until it gets an acknowledgement. And then accept a new service data unit from above and transmits that. Go back N can transmit several service data units at the same time. So I get 1, send it, 2, send it, 3, send it, and then I keep track of the acknowledgements that come back, right? So I have more transmissions ongoing at the same time in go back N. And to do that, I need to buffer. If I'm the transmitter, I need to buffer frames, service data units that I get from above. And we had this buffer is also called the send window, and the send window have space for a number of frames, WS frames, and we need to store at least n of those, the same n as in go back N here. And these frames then contain all the send window contains the service data units, so actually the frames which have not been transmitted but not yet acknowledged. And once we get acknowledgements, we can free up that space in the buffer and then accept new service data units from above. Okay, and that's called to slide the window, because that's the visual thing that happens. Okay, we will see an example of this later on. Okay, now we have talked about these two protocols, and we will talk about the third one today. But the question is, why do we have several different protocols, right? Typically, it's like this, that there is some trade-off involved in this. And here the trade-off is with simplicity of the protocol and also performance of the protocol. And we will see now that we would calculate two performance metrics which are quite related to each other. And it's called the effective data rate and efficiency of these protocols. And we will see that sometimes it's preferable to use go back N rather than stop and wait, and the opposite. And then there is this selective repeat that we will talk about later on, and show also that sometimes we want to use that. Okay, so again, remind us about the situation. We have an ARQ protocol, and protocols lives in layers. So suppose this is in layer N, and ARQ protocols could actually be in different layers, and there are reasons for this. But suppose that this one happens to be in the nth layer. Then there is a service provided by layer N, and that service is this error-free transmission of service data units. That is service data units as from the perspective of layer n, which is equal to the upper layer's PDUs. Okay. So the upper layer transmits PDUs, and it's actually doing that by pushing it down to us, and then it becomes a service data unit for us. Okay, so the effective data rate of the service, and this is the data rate which is perceived by the layer above. Okay, that is the number of bits that are in one service data unit. Okay, so the number of bits that I get from above divided with the time it takes to transmit that service data unit. And by transmitting, I mean all the time it takes from when I receive it, format that, transmit it, maybe retransmissions and so forth, until the time it's actually delivered up at the receiving end. Okay, so it's the time from where I get it from above at the transmitter until it's delivered up at the receiving end. Okay. So, and if layer n-1, the layer below us, has an effective rate r, okay, because what I do is then when I get the service data unit, I format that according to the ARQ protocol, but then I push it down to the layer below for transmission. So the layer below me has a certain effective rate also, and that is the data rate that I perceive. I live in layer n, I perceive some data rate, and I get it from above. And the ratio between the data rate that I deliver up to the data rate that I have below me, that is the efficient. How efficiently am I using the data rate which is below me to deliver data rate up? Okay, so that's the efficiency. So the efficiency is the ratio between the effective rate, that is the data rate that the layer above me perceives, to the data rate which I get from the layer below. And we can never increase this data rate. Right? I cannot transmit more bits per second than what the layer below me. I cannot deliver a data rate up in bits per second, which is higher than the bits per second that I can get from the layer below me. Right? There's a fundamental limit to this. Right? So if this is a 100 megabit Ethernet, for instance, I cannot, over this one, deliver a 1 gigabit service. I mean, it's impossible. Okay, so efficiency is always less than 1 here. So let's look a little bit on how to calculate this for stop and wait. So stop and wait performance. Okay. So remember, what we want to do is we want to calculate somehow the time it takes to deliver a service data unit. So we need some notion about what's taking time in this process. What one typically does then is to draw a timing diagram where we have the transmitter and receiver and see how different events at the transmitter and receiver results in that the service data unit is delivered. So let's draw a timeline here from the transmitter's point of view, and then we have a timeline for the receiver. So here we have time. Okay. So at some point in time, say at this point in time, the transmitter gets a service data unit from above and formats that and starts to transmit that. The first bit is now transmitted at this point in time, and the first bit of the frame will reach the receiver at this point in time. And then the last bit in the transmitted frame will be transmitted at this time, and then it goes over the channel, and then it will reach the receiver at this time. So the time between these two events is called the frame duration, TF. It's the time it takes to transmit a frame. And that has to do with how many bits there is in the frame and what the data rate is of the layer below me, right? Because I use the layer below me to transmit this. So these, what we transmit here is an information frame, and it consists of NF bits. The time between when the first bit is transmitted until it reaches the receiver, this is called the propagation time, or T-prop. Okay, and then the time until the last bit has arrived is then TF. Okay, the frame time is the same, of course. So what happens now is that the at this point in time, the receiver have received a complete frame. What does the receiver do then? Well, it looks at the check bits and see whether there is an error has occurred or not. So let's assume that no error has occurred. But to check the CRC and make these decisions, it takes a little bit of time. So some processing time here until we have completed the task of checking whether there is any error detection. So let's call this T-pros. So suppose there are no errors. The next step is then to transmit an acknowledgement back to the transmitter. So the first bit of the acknowledgement leaves the receiver at this point in time, and then at the last bit one leaves here. So this is the transmission of the acknowledgement. So this is an acknowledgement, and it consists of NA bits. The time to transmit the acknowledgement is called T subscript A. And the time over the channel is the same as before. It's a T-prop. Right. So from the transmitter perspective, it's now waiting for an acknowledgement after it's transmitted the frame. It waits for the acknowledgement, and the first bit of the acknowledgement reaches the transmitter here, and then the last bit here. And now the transmitter checks the CRC or whatever error detection there is in the acknowledgement, and if it has the right sequence number, it can go on and transmit the next service data unit. But this takes some time here before that could happen. So here we have some processing time again. Oops. Okay. And now, if everything is okay, now at this point in time, the transmitter can now accept a new service data unit from above, right? And then start to transmit that frame later on, like this. Okay. So any questions about this timing diagram so far? Okay. Okay, so the crucial time here is the time it takes from when the first bit of the service data unit is transmitted until we're ready to transmit the next service data unit. And this is called T0. It's also known as the reaction time, or turnaround time. Okay, and so what is we can calculate the turnaround time easily by drawing down this line here, and we see that in the bottom here we see that we have here also a T-pros at the end here. Okay, now, so if we want to calculate T0 here, it's easy enough to do that below here. We see that we have a T-prop, a TF, a T-pros, a TA, a T-prop, and a T-pros, right? We just add them together. So it's easy to calculate this. The thing is that, and we will see later on, that the time here from when the last bit of the frame has been transmitted until the end of, okay, so let me get rid of this. So here, we just moved it, we moved the processing time down here. Because what I want to do is I want to draw this part here. This part is when the transmitter to receiver link is idle. Okay, and we will see later on that this is what sometimes is causing bad efficiency for the stop and wait protocol, because here the transmitter is doing nothing while it could have potentially been transmitting data, but now it's just due to the protocol it's waiting for the acknowledgement. Okay. So let's now put some numbers onto all these variables here, the frame time, the processing time, and the propagation time. So the time for a frame, the frame duration, has to do with the number of bits in the frame duration, in the frame, NF, and then we divide through by R, where R is the bit rate, that's bit per second, of the layer below the ARQ protocol. Okay. Because remember, when transmitting this frame, what I essentially do is I take these bits and push them down to the layer below me for transmission. And the layer below me is capable of transmitting R bits per second. So the time it takes to transmit a frame is NF divided by R. So the higher the rate, the faster it goes. The more bits I have to transmit, the slower it goes. Okay. The propagation time is the time it takes for one bit or the first bit to reach its destination, right? Or any bit to reach from when it's transmitted until it reaches its destination. And the propagation time essentially has to do with the propagation speed and the length between the distance between the transmitter and receiver. And also if there is multiple hops, I mean nodes in between, there might be a network between the end nodes here, then there could be buffering delays inside the processing inside the routers that would add significant time to this. But in the simplest case, when we only have like a distance between the transmitter and receiver, which is D, and then we have some propagation speed, V, then the propagation time is just D divided by V. So to get some feeling for what this could be, on a fiber optical channel, this will be D divided by the speed of light in the fiber, which is actually a little bit less than the vacuum. So it's like maybe 2/3 of the speed of light in vacuum, which is 3 times 10 to the 8 meters per second. So if one calculates this a little bit, one gets that this is essentially D times 5 nanoseconds. So if we have the distance in meter, it's for each meter, it costs us 5 nanoseconds. So this is 5 nanoseconds, right? Okay. So if we have a kilometer, we have, what, 5,000 nanoseconds, 5 microseconds to transmit it. So this is some time, and if it's a very long distance, this could be significant. So if you know to transmit over a satellite link, it's quite a long distance, so that takes time. The processing time is hard to say what it is, but it is what it is. It depends on the hardware that we use and so forth. So and this is to check logic, error detection, assemble frames, general signal processing. D to A conversion, A to D conversion, things like that. It takes a little bit of time. Right? Sometimes this is negligible compared to other ones. Sometimes it's a sizable part of the overall delay. Okay. And then T0, the reaction time here, well, it's just to add everything together. And we see that we have 2 propagation times and 2 processing times. So it will be 2 times T prop plus T pros. And then we have the time it takes for a frame to be transmitted, and that is NF divided by R. Yes, a question?
The second processing time.
Yeah.
Are the 2 processing the same length? I mean, the first T process takes care of all the data that comes into the receiver, and the second one just takes care of the app. The app usually.
Right. So, for simplicity, we just think of them as being the same. But of course, they are not the same in practice, because not only is the task different, but the hardware could be different also. Yeah, but just to keep things simple here. Anyways, the time it takes for a frame is NF divided by R, and then we have also the ACK here, which is NA divided by R. Typically, the ACK is much smaller than the information frame also. Okay, so now we have the basic tools here to figure out what is then the effective rate, because the effective rate. And now I have a superscript 0 here, because now this is the best we can hope for when we have probability 0 of losing a frame. Okay, so what is that? Well, it's the number of bits in the frame, but not the entire number of bits, but only the bits that belongs to the service data unit that I got from above. So I get a number of bits from above, and then I stack on the headers and maybe the CRC bits and so forth. And the frame that I push down has length NF. So NF here includes the service data units and headers. So there is some overhead bits in here, N0 or NO bits. So the number of useful bits.
A question.
Yeah.
What was RF now again?
RF, it's NF.
No, R efficient or.
Okay, so this is the, this is the effective rate. Okay, so that's the data rate that the layer above me perceives. Okay, and the layer below me wants to transmit the service data unit or number of bits, and that takes T0 seconds to transmit that. So the number of service data unit bits is NF divided by, NF, and we subtract off NO, and NO is the header bits, the CRC bits, and so forth. And then we divide through by the time it takes to transmit that frame. And so that's the effective rate. Okay. So it's important that we understand why the effective rate is of this form. It has to do with the number of payload bits or service data unit bits here. And that is the total number of bits we transmit subtracted off the overhead bits. And then we divide through by the time it takes to transmit this. And it takes T0 seconds. Why does it take T0 seconds? It seems like it takes TF seconds here to transmit that. That's right, but we cannot transmit the next frame until we have reached this point in time. Okay? So it's not only the time it takes to transmit the frame per se that's important, it's the time from when the first bit is transmitted of a frame until the time when we can transmit the next frame. Okay? Because then we accept new bits from above at the transmitter. Clear? Okay. so by just putting in the numbers here and do some simplifications, we can write this as being the final result is R, and then times 1 minus, I'll just write it up what it is here. It's R, and then it's a fraction, 1 minus NO divided by NF, and the whole thing is divided by 1 plus NA divided by NF plus a little bit complicated expression here, R times 2 T prop plus T pros and the whole thing divided by NF. Okay, so it's just a few simplifications. I encourage you to do this at home, right? So we see here that the effective rate is this expression. So it's proportional to the rate of the layer below us. Okay? And whatever multiplies the rate below us is the efficiency by definition. So this fraction here, whatever is in red, this is the efficiency. And since we have 0 errors, it's n to the with this notation n0. Okay, and if we go into see and what is causing this efficiency to be large or small? So let's concentrate on what makes it small. It's something which is less than 1. So the first thing that makes this small is, of course, that we subtract off this. So it's n0 divided by nf, and n0 is the overhead bits, and nf is the total number of bits in the frame. So this is the penalty due to protocol overhead. How many header bits do we need, and so forth, in relationship to the total number of bits. So it's the fractional overhead, we would say. So this part is the protocol overhead, or protocol OH for overhead. Then we have two things in the denominator that makes the fraction small. And one is NA divided by NF. So this is the loss due to the transmission of acknowledgements, right? The bigger the acknowledgement is in number of bits in relationship to the frame, the worse the efficiency is. Okay. But the final and perhaps most interesting term is this one. So let's dissect that a little bit before interpreting. We see that the rate is here, the data rate of the layer below me. So that's interesting. And then it's 2 times this T prop plus T pros. So what was that again? Well, that has to do with these times, the propagation time and the processing delays. So if we take those together, they multiply, 2 times those multiply R, okay? So the greater R is, and the greater these processing and propagation times are, the worse the efficiency is, okay? So that delays could negatively affect the efficiency, that seems to be pretty clear. But it's also interesting that if we increase the data rate, we buy a more expensive Ethernet, whatever, that actually hurts our efficiency, which is not what we suspect, right, initially. And then everything is normalized with the frame duration here. So if we want to make this term small, what we want to do then is to make the frames large. But there is also a end to things. We cannot make the frames gigabits long, right? They're typically more like 1500 bytes for an IP packet or something like that. So it's more like a 1000 byte type of thing. It's not gigabytes of data. So there is, for various reasons, limits to how big we can make the frame. The propagation delay and the processing delay, what can we do about that? Well, the propagation delay, we cannot do a whole lot about that because that's physics. The processing delay, we can of course buy faster hardware, we can do that. If we include then also router delays and so forth in the propagation time here, we can make the routers faster. But at the end of the day, there is some processing propagation time that we cannot do much about. So for instance, when we have a satellite link, that will be dominated by the distance divided by the speed of propagation. That's it, right? So we cannot do much about this term here. And of course, we can select R by investing more or less into the layer below us. Okay. But it turns out that this type of ratio here, or actually product, we have here in the denominator product between rate and some delay. So this is sometimes called the delay bandwidth product. So delay is here, and R here is data rate, and sometimes it's called bandwidth in computer science, right? So it's a delay bandwidth product, which is then normalized with the frame length. So these things pop up, as we will see regularly here. So this is called, okay, so this is the loss due to delay bandwidth product. And we will see that these type of terms will show up in many different places. So any questions? If we would visually look at what's going on, so this is not very scientific, but if we would look at, say, we would plot the effective rate as a function of the rate of the layer below us. Okay, so we buy a more expensive Ethernet and we run our ARQ protocol over that. So what do we expect that the effective rate then? It would increase as a function of R. That's what we expect. And actually, it's not difficult to show that it does, but then at some point, the gain is of diminishing returns. So it's flattening out at some maximum effective rate. Which means that even if we increase the data rate of the layer below us, we are unable to use that in any good way. Right? And if we would plot the efficiency, if we would plot the efficiency as a function of rate, we get a similar curve, but the other way around. Right? So the efficiency goes down. And which is obvious because the efficiency is the effective rate divided by R, right? So the first curve gives the second one, or the second one gives the first one. So it's just two ways of looking at the same thing. Questions? Was this too slow? Too fast? Lagom? We love lagom. Okay, so the situation that we have been looking at is this one, where there are no errors. Okay, so neither the frame, the information frame, nor the acknowledgement is lost. So let's now look at the situation where the frame could be lost, but we still neglect the fact that the acknowledgement could be lost. And this could be motivated by saying that the number of bits in the frame here is much larger than the number of bits in the acknowledgement, meaning that if we have a fixed bit error probability on our line, then the probability that the frame is lost is much higher than the probability that an acknowledgement is lost. The more bits we have to transmit, the more likely that one of these bits are in error, and therefore the frame error rate goes up. Right? So for a fixed bit error probability, the more bits we transmit in a frame, the higher the probability that the frame is received in error. Right? It's just a fact of life. Okay, so what happens then if we assume that these frames are actually in error? So what's going to happen then is that if there is an error in this frame, there will be no acknowledgement, and we will have a retransmission of the same frame after the timeout time. And then we will have a new transmission, and maybe this one goes over the channel, or maybe this one is also lost. So actually we can be unlucky and lose multiple frames in a row, and then of course the time to deliver that frame also increases. So now, instead of having a fixed time from when the first bit is of a frame is transmitted until we can transmit the next frame, this is a random variable. And the random variable here depends on how many retransmissions we need to do. Okay. So let's calculate what happens then. So we introduce a random variable, and that variable is n subscript t. So this is equal to the number of transmissions needed to deliver a frame. Okay, how many times do I need to transmit a frame until it's delivered? If I'm lucky, I only need to send it once, right? So the smallest value nt can have is 1. If I'm unlucky, I keep on having 1,000 bad days, and 1,000 frames in a row are lost. As a matter of fact, there is no upper limit. So nt can be a number between 1 and infinity. So what is the probability for this? Okay, so this is, first of all, it's a random variable, right? So then what we would do to specify that random variable is to calculate the probability that nt takes on a number I, an integer I. Okay, so what is this probability? Well, if we say that nt is equal to I, say 3, so what is the probability that nt is 3? Well, that means that we have transmitted the same frame 3 times. Okay, 1 lost, 2 lost, third one delivered. Right? So 2 losses and 1 delivered. If it's 4, it's 1, 2, 3 losses and 1 delivered. In general, there will be a probability of, if this is the frame error probability, we have I minus 1 such events, consecutive events. Okay, so the probability for I minus 1 consecutive losses of the frame is Pf, the probability of an individual frame to be in error, raised to the power I minus 1. Okay, and then the last time, the final time, the frame went through, and it goes through with the probability 1 minus the probability that it's lost. So 1 minus Pf. Okay, so this is the probability that nt takes on the value I, exactly I. Does it make sense? Okay. And this one we can calculate for I equals 1 when the first frame goes through, 2 when it takes 2 transmissions, so 1 failure, 1 success. And then we can keep on doing this for infinite many, or for any I greater than 1. Okay, So the probability okay. So why do we want to do this? Well, this one tells us how many timeouts we need to wait until the frame has been delivered. So we had a question.
Should we have a break?
Thank you. It's time for a break.